Hello, everybody. Let me get chat out again. I will start the tutorial again afterwards. Yes, pop out the chat, please. I got the chat out. Here. This comes here. Yes. Okay. We are on the camera section. Yes, I will try to start my code. What have we done in the last um the last stream? Enrico right now, but I will play review of my code. I think I had a camera class here somewhere, and my problem was that I couldn't start the camera. Yes, this should have worked, but it didn't. So the camera should have two arguments, which are an up vector, another up vector. Yes, we can get them now. This is weird. Yes, we can define a camera right now, which need two GLM vectors, which are called origin and where is the camera.h? Should be then, yes, camera origin and camera target. Camera origin should be a little bit front, so we should go like 003, 003, and the camera, what's the other one again? Target. Camera should target to the origin. So we type 000. Yes, and afterwards, using this camera, we are going to define the view vector. Do you see it, guys? Let me check. Do you see the camera function? Yes, you see it. Let me do this. Content. And see. Yes, this is good. Okay. Ish. It's okay. The camera is a little bit big, but I don't care. Let's see. How does it look like? What do we have here? We have created our camera. We will create a view vector with this camera, and this is going to be like this: camera get view. Oops. Get view. This should be it. All the functions will then be handled in the view. Oh, sure. Oh, sure. I should, yes, view equals look at camera origin. So I will not type it here. Not type it here. This view equals to this. Look at whatever. It's camera origin. This should camera origin. And where is this function, may I ask? Okay. Yes, this is in this what that we want, but why do we get error? Do we have to call big float here? Don't think so. Maybe we should call 0.f. Could be also okay. Let's just go up and front and call, up is, what was it? Up is 0, 1, 0. This up equals vectory 0, 1, 0 point f, 1 point f, and 0 point f. Okay, what's this? I don't want this. Get out. You get out. Front is 0, 0, minus 1. This front equals vectory as 0, 0, and minus 1f. Okay, and the camera view looks like this, and the camera right should then look like this. And I don't like this either. I will just say camera right here and say this camera right equals to normalize blah 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 blah. This is a declaration now, so we have our private fields, we have our constructor which initializes our private variables. Was this too few arguments? B. I knew it. I knew this wasn't a thing. ChatGPT, man, you're kidding me. Are you kidding me, ChatGPT? Control camera. Then gun. What the? Can I? Sidebar, please. Uh-huh. There is no function. No function. GLF. I was so happy to hear that, by the way, that a function like that exists. Window is with only one argument. With only one argument. You're correct. Apologize for the oversight. Uh-huh. Okay. I mean, you're still using the same thing. You are still using the same function, my guy. I mean, okay. What is this, bro? This is such a weird guy. Let's just do if else. If glfw get key from window with w equals glfw press, we will move up camera. This is not a switch statement after all. Please leave me alone. We are going to set the camera origin. You can flip off. We are going to set, yes, tab this once. This should be fine. Let's see. Should be fine. So choose this, can't click Control, let's click Shift, Y, Control doesn't do it, Windows doesn't do it, Alt doesn't do it, Control Alt does it. So delete them all, one go, and tab them and type glfw get key from window. Yes, type this and equals glfw with a press, and yes, this should open. bracket, here a bracket, and type enter. What happened? Each and every one of them got entered. Okay, we opened the bracket. Now we just have to close it. Here one. And here another one. Here another one. And close this. We don't need this. We don't need this. Tab these, tab, untab twice, untab, backspace, yes. Process input, I don't like it to call process input, but I want to call move camera, save it. Yes, this is good. Yes, yes. So get input window, move camera window, yes. After defining the camera, we can say move camera. Of course, we have to call camera. Okay, oh. Dot move camera from window. Yes, that should be it for the view vector. We created those. We did walk around. Movement speed, what it is, I don't know. As of now, I will read it. Okay, movement speed. Currently, we use the constant value for movement speed when walking around. In theory, this seems fine, but in practice, people's machines have different processing powers, and the result of that is that some people are able to render much more frames than others each second. Whenever a user renders more frames than another user, he also causes processing more often. The result is that some people move really fast and some really slow depending on their setup. Okay. When shipping your application, you want to make sure it runs the same on all kinds of hardware. Okay. Graphics applications and games usually keep track of a delta time variable that stores the time it took to render the last frame. We then multiply all velocities with this delta time value. The result is that when we have a large delta time in a frame, meaning that the last frame took longer than average, velocity for that frame will also be a bit higher to balance it all out. When using this approach, it does not matter if you have a very fast or slow PC, the velocity of the camera will be balanced out accordingly so each user will have the same experience. Okay. So, this is going to be called I'm guessing that this is going to be called in each loop, step. So we are just going to type float delta time here equals to 0 and float last frame equals to 0. And the current frame will then be determined by the GLFW. I mean, I can just move this function to line 287, and I will simply then say delta time equals current frame, which is time value, minus the last frame. At the start it's 0, and afterwards it's time value. Sorry, it's time value. Okay. So the camera speed will be 2.5 times this camera speed. So we can set camera speed here to our camera. The default camera speed should be 1.0 equals 1.0 f, and save. Camera speed is not uninitialized. So we initialized camera speed, camera target, camera origin, up, front, camera right, and view. Okay, we have all. And here we should say camera set camera speed to a value which is 2.5 f times delta time. I'm just following the specifications here. I will read now what it is. Okay, we understood what delta time is. It is a simple it's a simple function to determine the time between the current frame and the last frame. So it determines the speed of the computer, I would say. Let me adjust the camera like this. And afterwards, we have set the camera will now move at a constant speed of 2.5 units per second. Together with the previous section, we should now have a much smaller and constant camera are moving around the scene. This doesn't seem so consistent. Okay, let's start it. I'm really ready with it. Oops. Save. Okay. Can't move my camera. Field. I can't move my camera. P, field, P, field, P. I can't move it. Why can't I move it? The view is set. The MVP is set. The MVP is set here too. I mean, we can transport the and transform the what do you call the model? What's this model here? Model is 1.0. What is this model? I mean, I'm sure I've implemented it right. Okay, view. I don't like it. Okay. Ground, look at process input. Can it be? It is normalized here. Let's see. And D. Now we what? the resulting right vector. If you don't normalize this vector, the resulting cross product may return differently sized vectors based on the camera front view. Would not normalize the vector, we would move slow or fast based on the camera's orientation. It's better concept. We don't move at all right now. Don't move at all. Set camera origin, this camera origin minus camera right front times camera speed. I mean, camera function should work, right? If you change the camera position, I don't think anything will change. 6. Okay, let's see after. Let's go here. Okay, this seems a little bit different from before, but it still does not process my input. As you can hear, I'm cranking up that W button and I don't get closer. Or I don't get farther away. Let me, for debugging purposes, let me just print the cout, print the view matrix here. I want to see how it looks like. View and do. Okay, can let's say address of view. Don't want the address of. Just want to type for integer e equals 0. E is less than 16 and works by 1 by 1. Let's code the view e and would work. Let's do this then. View to take the address of view and edit. Take the address of view, please. Take the address of view like this, add e to it, and get the value. Not. And this is a float. 16 floats. Just give me the floats. Type it like this. What happens? Let's see how it's happened. How can I print the mat for G? So this is a float pointer. Okay, let's call float pointer view pointer view get low value pointer. This is pro. There is no function value enter in GLM. Generates a pointer to the say this, then you say right. I simply type I the I. Is it really alright like this? Is it alright like it's not? So we have to go to for loops. This is the same, it's alright. It is alright. 3 0 1 2 3. That's it's J plus plus. Open the bracket. Q V J and E. Handle is E for yes. Let's Q it, and we're ready to go. We're going to see if our matrix changes. Doesn't. Doesn't. So either my what do you call it? My move camera method doesn't work, or I don't know. This move camera should move the camera. Look at camera origin, camera target, and up the camera origin. Here again, not a. This is not a the constant variable. Afterwards, just type the camera origin, you know? That camera origin here, code camera origin. Let's say is front. What is front? Front is -1. So please type the second. Let's go. It's not open. Start it. Type. It should minus. Okay. Or because we started it with 4. Stop. I'm typing W. Still 4. It is still 4. So the move camera function doesn't work. What happens if I what happens if all the camera, where is it here, camera here. I will do camera here. To the E. Camera like this camera, camera, camera. Cannot camera. Okay. Let's just call it this. There it is. Again, camera. Okay. Does it work now? Oh, doesn't. It does not. Okay. Let's move this to this. So, wie äh, Hey, but where is get input here? Guys, start. It doesn't change, does it? It's not. Does change actually. I see a different values here. Like this. When I type W, I see 4s and 3s and 5s and I don't know what. So it does change. It doesn't update. 004, 000, view, get camera, get view. Projection, view matrix doesn't change. Why? Why doesn't it change? Camera, let's just call view here. See what. Yes. Origin is set. Can it be? Maybe we should. Okay, I know what the problem is. We don't change the view vector at all. We should change the view vector each time we the origin. So it only calls it here once. That's it. I didn't need to type to go get. Okay. I mean, after each of something changes. Also change. Am I right? Yes, I am right. No, that's all. View should be cool. God. Okay. Here it is also done like that. Camera pause. And afterwards it should calculate from the camera pause. Yes, calculation is done from the camera pause. So yes. Okay. Now it should work. It doesn't. Doesn't work. It's freaky. It does not work. Why doesn't it work? Change it. Value. Blah blah blah. The camera speed is 0.5. I don't care. Let's try. It doesn't change. That's so dumb. It simply comes back again to the. Do you see it? We see 1.5 and we see 4. Okay. Let's view. Camera get view. Get view directly returns the view. And view is changed here. This is so weird. The camera origin is set like that, and after the camera origin is set, okay. Of course, I'm creating the camera in the loop. Okay. So it resets. I should create the camera out of the loop. Such a dumb error. Yeah, this is. Yeah, at least we get something. Where is my fan? Come on. At least we get something. One tap. Is it? It's too fast even, no? Is this? Feel it. One tap. It's gone. Two tap. One. Oh, wait. Where are you? It's lost. Okay. What's this metric? Does it set twice? Camera get view. I don't need you anymore. I don't want to set the camera speed like this actually. I just don't care. I want 5. 11.5. Minus 16. 14. Minus 3.5. Boom. It's broken. Boom. Boom. Camera is moving. It's broken. It's too fast, no? Too fast, too furious. Bang. Bang. Where are we? I can't see. Where are we? It's lost. It's back again. Yes, the camera works, guys. Feel it, the pizza. Camera works. We set. I don't know, this seems sketchy here. Look around. Only using the keyboard keys to move around isn't that interesting, especially since we can turn around, making the movement rather restricted. That's where the mouse comes in. To look around the scene, we have to change the camera front vector based on the input of the mouse. However, changing the direction vector based on mouse rotations is a little complicated and requires some trigonometry. If you do not understand the trigonometry, don't worry, you can just skip to the code sections and paste them in your code. You can always come back later if you want to know more. Let's see, what are the Euler angles? Euler angles are three values that can represent any rotation in 3D, defined by Leonhard Euler somewhere in the 17th. 17. There are three Euler angles, pitch, yaw, and roll. Pitch is this, yaw is like this, and roll is like this. It's a difference. A pitch is like this, or roll is like this, and pitch is like this. The pitch is the angle that depicts how much we are looking up or down, as seen in the first image. The second image shows the yaw value, which represents the magnitude we're looking to the left or right. The roll represents how much we roll, is mostly used in spaceflight camera. This spice is it Dune? Each of the Euler angles are represented by a single value, and with the combination of all three of them, we can calculate any rotation vector in 3D. For our camera system, we only care about the yaw and the pitch value, so we won't discuss the roll value here. Given a pitch and yaw value, we can convert them into a 3D vector that represents a new direction vector. Let's see. Okay. The basic case. Let's start with a bit of reflection and check the general right triangle. Okay, so this is sin y, sin the cos x, and hypotenuse. This cos. I think this is the gamma x. This is cos is like this. The sin opposite direction. That the adjacent side's length is cos x. adjacent sides. Length is cos x divided by hypotenuse equals cos x divided by 1 equals cos x, and the opposing side's length is sin y divided by hypotenuse, because it is this. Sin y. Okay, this gives us some general formulas for retrieving the length in both the x and y sides of the right triangles, depending on the given angle. So this is sin y, this is cos y. Okay, let's use this to calculate the components of the direction vector. Let's imagine the same triangle, but now looking at it from a top perspective with the adjacent and opposite sides being parallel to the x and z axis, as if looking down the y axis. So, perspective. I don't understand what that means. If you visualize the yaw angle to be the counterclockwise angle starting from the x side, you can see that the length of the x side relates to cos yaw. Similarly, how the length of z side relates to sin yaw. Okay. Take this knowledge and a given yaw values, and use it to create a camera direction vector. The direction is radians of yaw. So we define the yaw. Okay. So we can get a 3D direction vector from a yaw value. I'm just going to the camera code 3 direction, and the x is radians yaw from cos. This is cos yaw, this is sin yaw. Okay, I got it. And the y is defined like how? Okay. The x and z are defined by yaw, because it's standing perpendicular to the y. So we can only, and the pitch comes in the y. Okay. I think I get it. But I would think, why do we have x? I see. The triangle is the same, but it is parallel to, okay, it's like the plane here. You see plane here, like plane. It is it stands 90 degrees to the y and parallel to the x and z. Like it's on the it stands like it's on the x and z plane. So we can define the yaw, sin yaw, and cos yaw using the x and z. Okay, I get it now. But why does it doesn't stand perpendicular to the x-axis here, but why can we type x and z here? As if we are sitting on the xz plane. Here, where is z? I don't know why I get why we set x and z by cos and sin. I really don't get why we set y like this. Okay. However, from the pitch triangle, you can also see the x sides are influenced by cos pitch. So we need to make sure this is also okay. This is also part of the direction vector. With this included, we get the final direction vector as translated from yaw and pitch Euler angles. Cos GLM radians yaw times GLM. Okay. This gives us a formula to convert yaw and pitch values to a three-dimensional direction vector that we can use for looking around. Okay, I will set it in the constructor again. The direction vector is set by the yaw and pitch angles, but the yaw and pitch are loads. Yes, the direction and this yaw equals to what? Minus 90, let's call it. And the pitch. Fine pitch. After we even define pitch here. Let's say 89. Not type is 89. And the direction is then created from this. I will just type it. The vectory from cosine cosine of the radians of the yaw times cosine of the radians of the pitch. And second one is sine of the radians of pitch. And the third one is sine the radians yaw times cos GLM radians pitch. I really don't like this. So I will call I will make a method out of it. Set direction void set direction. We don't need anything. We simply say this one. Direct. Yes, this is ready. The method direction setting is ready. We need to simply set the yaw and pitch. Afterwards, we get. Okay, we are so close. Mouse input. We get GLFW. Vertical mouse movement affects the pitch. So the horizontal mouse movement. This is weird. So it's going to be like. It's going to be like open world. I don't know. First person shooter. I don't know, like that, or am I missing something? The more we update the pitch or yaw value, and thus the more camera should move. First, we will tell GLFW that it should hide the cursor and capture it. Capture the cursor means that once the application has focused, The mouse cursor stays within the center of the window on application loads, focus or quits. And do this one with one simple configuration. W set input mode, window glfw cursor, glfw cursor disabled. After this call, wherever we move the mouse, it will be visible and it should not leave the window because it's in the window. This is perfect for an FPS camera system. To calculate the pitch and yaw values, we need to tell glfw to listen to mouse movement events. It's by creating a callback function. The following void mouse callback, set cursor pose callback. Okay, here X pose and Y pose, Y pose represent the current mouse position. As soon as we register the callback function with glfw each time the mouse moves, the mouse callback function. Okay. So let's see. Create a mouse callback function. Void mouse callback from the glfw window. The positions of the mouse bypass. Implement afterwards. Here. First of all, we have to set the callback method. Where did we set it for the first method created? glfw set frame buffer size callback. When handling mouse input for a fly-style camera, there are several steps we have to take before we are able to fully calculate the camera's direction vector. Calculate. Come here, I suppose. W set cursor callback and no mouse callback. Okay. When handling mouse, okay, calculate the mouse's offset since the last frame. Add the offset values to the camera's yaw pitch value. Add some constraints to the minimum, maximum. Calculate the direction vector. First step is to calculate the offset to the last frame. First, I have to start the last mouse positions in the application. Initialize to be in the center of the screen for 300 because we have 800 by 600. Okay. Where can I set those? Set those loop. Float last x equals 400, last y equals 300. And the xpos. How do we get the xpos? And in mouse's callback function, we calculate the offset. This goes. And in the mouse callback function, then void mouse callback with window window a double xpos, double ypos. This should define. Should call float x offset by subtracting xpos from the last x, the y offset Okay, this should be negative values, but should tell where the mouse is, and yes. Last x that equals the x pos, and the last y equals the y pos. And the sensitivity. Okay, I just get it. Okay. Let's call load sensitivity here. Load sensitivity 0.1 and offset by offset, and let's call if the key get key window key, I don't know, plus maybe plus key plus is plus minus there minus. Why is there a minus and not plus? W press V set sensitivity equals sensitivity minus equals 0.01 f plus 2 plus, please let that be asterisk maybe, no, but page up, man, come on, page up, there is page up, I know there is. Okay, plus let's make this page down. So known. Yes, callback should be like this, and the yaw and pitch. This plus equal, what am I doing? X offset. The pitch by offset. I'm coming in a bit. I need to get some water. Hello, I'm back again. Back again. So. So this time I want to have set functions. Because right set pitch with a float pitch, and this pitch if pitch if let's first call this pitch equals pitch, and afterwards if call this, if this pitch is greater than, don't see it, I hate this, don't see it, this pitch is greater than 89 and we call it pitch, this pitch is 89 load, and that this, if this pitch is smaller than less than minus 95, then we call it minus 95. The yaw doesn't need it, so we call set pitch here, camera set pitch, camera equals camera dot pitch plus y offset. Yes, the fourth and last step is to calculate the actual direction vector using the formula from the previous section. This to camera front here, this front, this is for the front, normalize direction. Okay, and after we set the pitch, we should also set direction. Set direction. And we should also say set yaw here with a yaw value, and it's called camera this yaw plus equals yaw. This also calls the set direction method. Direction. And in the set direction method, we should call front equals to normalize. Okay. Set pitch camera, set yaw. With offset, of course. Yes. So this computer direction factor then contains all the rotations calculated from the mouse's movement. We should also look at how how is it included in the lookat function? Okay. Camera pause plus camera on. Okay, I didn't know that. Camera pause plus camera origin plus front. Look at here should also plus. Where do we even use the this is direction. Okay. This is a weird camera. I should clean this up after the tutorial. The dirty code. So okay, we have implemented it. Mouse input, did it, we did pitch, whatever. Camera front, we have done it here. Okay, the first mouse, what is this? This computer direction. Okay, if you I'll run the code, you will notice the camera makes a large sudden jump whenever the window first occurs. The cause of this for the sudden jump is as soon as your cursor in the mouse code with an X pose, Y pose equals position equals to the location your mouse entered the screen from. This is often a position that is significantly far away from the center of the screen, resulting in large offsets and thus a large movement jump. Circumvent this issue by defining a global bool variable to check if this is the first time we receive a mouse input. If it's the first time, we update the initial mouse position to the new and Y values. The resulting mouse movement then used enter the furnace to calculate offsets the file comes. Ah, okay. Okay. So simply find this is a dirty code. I don't care. We define a bool variable here. Bool flow of bool first mouse true, and here in the mouse callback, if this is the first mouse we are using, then do this, do that, vada, do this, yes, expose, whatever. See again if it's if it's still the first mouse, do this, Y pose, and set the first mouse to the false, to the value false. Zoom. I don't care for the zoom right now. I really don't care for the zoom right now. Let's see. Okay. Okay. Can see it. Let's. The sensitivity. Okay. This looks nice. Weird man. Okay, we get it. We are ready. We have finished the first getting started chapter. Review. We know what all of these are. Yes, by now we should be able to create a window, create and compile shaders, send vertex data to our shade. Hello, it's fine. Draw objects, use textures, understand vectors and matrices, and combine all that knowledge to create a full 3D scene with the camera to play around with. Phew, that's a lot. You learned these last few chapters. Yes, try to play around with what you learned, experiment a bit, or come up with your own ideas and solutions to some of the problems. As soon as you feel you got the hang of all the materials you discussed, it's time to move on to the next lightning chapters. I hope you get better, I guess. This is lightning. Lightning chapters. These are a bit advanced, but I think there's nothing we can't comprehend. Basic lightning. This is ambient light. This is the science stuff. The behind this and the coding. This is the science stuff, but you'll be fine. And I am feeling happy and excited to delve into these chapters, sections. And that's it for today. Thank you everyone for joining me. Have a nice day, have a nice evening. See you later, alligator. And this is OpenGL.